Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, let's unpack this, because I want you to imagine trying to force a physical wave of gas and dust through the interstellar medium at like 1,220 kilometers per second.
Yeah, that's not just fast, that's a speed that physically breaks things.
Right. We're not talking about a beam of light or a subatomic particle here. We're talking about a macroscopic shockwave made of baryonic matter. Just regular gas and dust.
Exactly. And if you actually sit down and calculate the thermodynamics of pushing material through the vacuum of space, well, in the near vacuum, at that velocity, the physics just completely falls apart.
Because it's not empty space.
Yeah.
Right. There's friction.
Right, there is. The kinetic energy involved would cause the gas to heat up to the point of turning into basically a superheated plasma. It would radiate immense amounts of X-rays.
So it would just cook itself.
Completely. It would unbind the structural integrity of whatever medium it was traveling through. You wouldn't get a neat, ordered structure at the end of it.
It would just violently disperse into nothing.
Yeah, the thermal dissipation alone would tear the structure apart long before it ever had a chance to stabilize. At 1,220 kilometers per second, you are looking at ram pressure forces that would strip a galaxy completely bare.
Wow. Okay, so it's a velocity that directly violates the fluid dynamics we observe in space. But, and here is the crazy part, that is exactly the mathematical corner astrophysicists found themselves backed into recently.
Yes, they did. We observed a structure in the cosmos that, according to our classical models of gravity and collisions, demanded that impossible speed limit to exist.
Which brings us to the anomaly itself, the object that is forcing this entire revaluation of the universe. It's LED 1313424, but astronomers affectionately call it the Bullseye galaxy.
And it is a very fitting name. When Mion Pasha and his team at Yale University published their observations back in 2025, they didn't just find, a slightly weird galaxy.
No, they found something that completely breaks the rules.
Right. They found a structure that basically shouldn't exist under the classical paradigm of astrophysics. We are talking about a galaxy characterized by 9 distinct, perfectly concentric rings of glowing material radiating outward from its center.
9 rings, like a perfectly formed 9-layer wedding cake, just floating in the middle of a messy, chaotic kitchen. It just begs the question, who or what baked this?
Exactly. It is an extraordinary morphological profile.
Yeah.
I mean, when we look at typical galactic structures, we expect spiral arms, like our own Milky Way.
Where things are sort of swirling and messy.
Right, where density waves propagate through the disk, creating these trailing arms of star formation. Or we see elliptical galaxies, which are essentially featureless, randomized swarms of stars.
Just a big fuzzy blob.
Yeah, exactly. But a concentric ring structure implies a highly localized, highly symmetric mechanism. Finding one ring is rare, but, it's mechanically explainable.
But 9.
Finding 9 stacked with that level of geometric precision. That challenges the foundational models of how galaxies evolve.
So the mission for today is to really pull apart the physics of this Bullseye galaxy. Because to explain how those 9 rings got there, we basically have to entirely discard the classical model of galaxies.
We do. We have to throw out the idea of galaxies as giant pools of gas just responding to physical collision.
And we have to cross over into a framework where quantum mechanics, which are the rules governing tiny subatomic particles, are actively dictating the macro structure of a galaxy that's hundreds of thousands of light years across.
Which is mind-boggling. We are looking at a potential bridge between the microscopic quantum realm and macroscopic cosmological structures.
So the Bullseye galaxy isn't just a weird space picture.
No, not at all. If the prevailing theory holds, this galaxy is a galactic-scale quantum laboratory. It provides observational evidence for stuff we previously thought we could only isolate in, like super-cooled lab environments on Earth.
Okay, to really grasp why finding 9 rings in 2025 caused such a crisis, we need to look at how astronomers historically explained ringed galaxies. Like, what was the baseline?
Well, the baseline was established way back in 1941. That was the discovery of the Cartwheel Galaxy by Fritz Zwicky.
Zwicky was kind of a legend for finding weird stuff in space, right?
Oh, absolutely. He was a pioneer in identifying structural anomalies. When he observed the Cartwheel Galaxy, It presented as this dense central hub surrounded by a massive luminous ring of young blue stars.
And it had these faint spokes connecting them.
Right. It was a radical departure from the normal sequence of spiral and elliptical galaxies, and for decades, the cartwheel served as the absolute archetype for what we call collisional ring galaxies.
And the model they came up with to explain the cartwheel made total sense at the time. It's the drop-through collision theory.
Yes. The idea is that a smaller, really compact companion galaxy plunges directly through the center of a larger disk galaxy, like a bullet going through an apple.
So it's a gravitational perturbation model. The smaller mass punches through, creates a sudden, localized spike in gravity at the center.
Exactly. And as the smaller galaxy exits the other side, that gravitational spike vanishes. This sudden shift triggers a massive density wave.
So the material in the disk gets pulled inward first, and then it kind of rebounds outward as this concentrated ring.
That's a perfect way to describe it. As that density wave travels outward through the interstellar medium, it compresses the surrounding gas and dust.
And when you compress gas in space, you get stars.
Right. It pushes the gas beyond what we call the Jeans mass limit, which triggers a localized wave of star formation. So you end up with this glowing ring of new stars expanding outward.
It's basically the leading edge of a gravitational ripple, like dropping a rock in a pond.
Yes, a very, very big rock. And the math for the drop-through collision works beautifully for the cartwheel galaxy.
The numbers actually line up.
They do. The velocities of the expanding gas correlate perfectly with the mass of the intruder galaxy and the time frame of the collision.
And over the 80 years following Zwicky, we found other examples, right? Like Hoag's object.
We did. Hoag's object exhibits a similar ring morphology. We'd occasionally find galaxies with 2, maybe even 3 rings.
Which you can explain by, like, a secondary ripple.
Right. It can be modeled by a complex, oscillating drop-through event, a secondary density wave reflection.
But the underlying mechanism for all of them remained collisional. It was kinetic, brute force physics. A smaller object hits a bigger object, ripples move outward.
That was the consensus from 1941 all the way until 2025. It held because the observations hit the parameters. The waves had enough energy to propagate 1 or 2 rings before friction dampened them.
Okay, so then Imad Pasha's team points their instruments at Liadai 1313424. And they don't see 1 or 2 rings. They see 9.
9 concentric structures.
I want to pause here. How do they even verify that? Because a 9-ring structure at that distance could so easily just be a smudge on the lens or an optical illusion from gravitational lensing.
That's a great point. The Yale team didn't just look at a photograph. They utilized deep spectroscopic imaging to confirm the morphology.
So they analyzed the actual movement of the gas.
Exactly. By measuring the redshift and blueshift of the molecular gas, they could track the rotational velocity and the radial expansion of the material in those rings.
Wow. So they proved it wasn't just a trick of the light.
Right. The data confirmed these were distinct, physically coherent rings embedded right within the galaxy's disk, sharing the exact same rotational kinematic.
Okay, so the rings are real, and the immediate scientific reflex is to use the old tools. The assumption was, well, we have rings, therefore we must have had a collision.
They applied the drop-through model. But to generate 9 distinct rings, you need a highly specific set of initial conditions.
You'd need a massive intruder galaxy, a perfectly perpendicular hit, and a very tight timeline for the waves to ripple out.
The initial hypothesis suggested this colossal impact event happened approximately 56 million years ago. The logic was that a single energetic collision triggered a whole series of reverberating waves.
But that is where Pierre Sikivi and Yuxin Zhao at the University of Florida enter the picture, because they look at that 56 million year timeline and they run the math.
And the model instantly falls apart.
Yeah. Tell us why.
What's fascinating here is that Sikivi and Zhao calculated the necessary phase velocity of the outermost ring. If a single event 56 million years ago created all 9 rings, then that outermost ring must have traveled from the center to its current position in exactly that time frame.
Which brings us right back to that speed limit problem we opened with. For that distance to be covered in that time, the math demands a speed of 1,220 kilometers per second.
And let's revisit why that fluid dynamics problem is fatal. The interstellar medium is a fluid. It has density, temperature, pressure.
So a wave moving through it is essentially a sound wave.
Exactly. And the speed at which a wave can travel is strictly limited by the sound speed of that medium.
And in a typical galaxy, what is the speed limit?
The sound speed of interstellar gas is maybe 10 to 30 kilometers per second. Even in highly energized regions, you might push it slightly higher, but you are nowhere near 1,000 kilometers per second.
Right, so going back to our rock in a pond analogy, you drop a boulder in a lake, you expect ripples to move at a leisurely pace. But if you drop a rock and the ripples shoot out at the speed of a fighter jet...
You wouldn't think, wow, that water is fast. You'd think, is this pond actually made of water?
Yes. You'd question the medium itself. Because if you force a wave at that supersonic speed, you flash heat the gas.
You do. It turns into X-ray emitting plasma. It would literally boil the interstellar medium right out of the galactic disk. You'd be left with a sterile, dead galaxy.
Definitely not a beautifully structured series of glowing star rings. The medium just cannot support it.
Sikivi and Zhao proved definitively that a classical collision cannot physically produce those 9 rings without violating thermodynamics. The wave would die out long before reaching the outer edges.
So when the math so directly contradicts the observation, you have to question everything. If a physical shock wave moving through gas can't create these rings, then they aren't ripples from a crash.
Right. They aren't kinetic ripples at all.
So the structure of the galaxy must be dictated by something else entirely, a different underlying force.
And this requires a massive pivot. We have to stop looking at the baryonic matter, the visible stars and gas, and start analyzing the non-baryonic mass.
The stuff that actually dominates the gravitational environment? We have to talk about dark matter.
Yes, the invisible elephant in the room.
Now, I want to frame this carefully for you listening. Dark matter sometimes gets a bad rap, like it's just a catch-all plug for whenever our gravity math doesn't work. But it's actually a rigorously tested concept.
It is. The empirical foundation goes back to Vera Rubin's work in the 1970s. She observed galaxy rotation curves.
Right, and based on standard Newton physics, we thought the stars at the edge of a galaxy should orbit slower than the ones near the center.
Because the further away a planet is from the sun, the slower it orbits. We assumed galaxies worked the same way since most of the visible mass is packed into the center.
But Rubin found something totally different.
Her data showed that the rotation curves were flat. Stars at the very edge were orbiting at the exact same velocity as stars much closer to the center.
Which means there just isn't enough visible stuff to generate the gravity needed to hold on to those fast-moving stars.
Exactly. Without an unseen source of mass, those galaxies should have literally flung themselves apart through centrifugal force eons ago.
Now, just to play devil's advocate here, why do we jump straight to invisible particles? What about MAMND modified Newtonian dynamics? Doesn't that say we just need to tweak how gravity works at the edges of galaxies?
MMND is a really fascinating theory, and it does successfully model the flat rotation curves of some individual galaxies.
But it has limits, right?
Significant limits. MOND applies a universal modification to gravity. It smooths out the gravitational potential. It struggles to explain highly localized, complex substructions.
Or things like the bullet cluster, where the gravity is separated from the visible matter.
Precisely. Because MOND basically just says, gravity is stronger out here. It does not provide a mechanism to create highly specific concentric geometrical rings.
You can't get sharp ridges of gravity just by tweaking a formula. You need actual localized mass.
Right. You need a physical substance that can clump, structure itself, and exert localized gravitational wells. MOND can't herd visible gas into 9 distinct rings. We need particulate dark matter.
Okay, so we're operating under the standard model here. Ordinary matter, everything we can see, makes up maybe 15% of the universe's mass.
And the remaining 85% is non-baryonic dark matter.
And it's not just floating around randomly. It organizes into these massive spherical halos, right?
Yes, the dark matter halo is the primary architectural component of any galaxy. The visible glowing disk of stars we see is really just a tiny secondary structure sitting inside a massive invisible sphere.
Kind of an existential thought. We are the weird, rare stuff in the universe. The dark matter dictates the rules.
It holds the whole system together. But, as you were hinting at earlier, a generic smooth sphere of dark matter still doesn't explain our 9 rings.
Because a featureless blob just provides a uniform pull. It wouldn't make stepped geometric rings.
Exactly. Which is why Sikivi and Zhao didn't just invoke generic dark matter. They relied on a very specific theoretical flavor of dark matter, the axion.
Okay, let's really dig into the axion. Because it's amazing to me that it wasn't even invented to solve the dark matter problem in the first place.
No, it was theorized to solve a completely different crisis in quantum physics called the strong CP problem.
Right. So what is the strong CP problem?
Well, it's a discrepancy regarding the strong nuclear force. The math of quantum chromodynamics suggests that the strong force should violate a principle called charge parity symmetry.
So basically, interaction should look different if you swap particles for antiparticles and reflect them in a mirror.
That's a good way to visualize it. But the problem is, in every single lab experiment ever done, the strong force preserves that symmetry perfectly. The math says it should break, but reality says it doesn't.
So physicists had to fix the math.
Right. In 1977, Roberto Pache and Helen Quinn introduced a new symmetry to the equations to fix it. And shortly after, Steven Weinberg and Frank Wilczek realized that this new math would create a brand new, incredibly light, electrically neutral particle.
And Wilczek named it the axion.
Yes. And while it was invented to fix the nuclear force, cosmologists quickly realized that if axions are real, the Big Bang would have produced unfathomable amounts of them.
They're light, they barely interact with normal matter, they're stable. They are the perfect candidate for dark matter.
But what makes axions fundamentally different from older dark matter candidates like WIMPs is their quantum classification. Axions are bosons.
Okay, this is the heavy science, but it's the critical juncture. The difference between a fermion and a boson is the whole key to the Bullseye galaxy.
It is. All particles in the universe fall into these two categories based on their quantum spin. Fermions like protons, neutrons, electrons have half-integer spin. They obey the Pauli exclusion principle.
Which means no two fermions can occupy the exact same quantum state at the same time.
Right. It is literally why matter has volume. Electrons in an atom stack up in different shells. They refuse to cram into the lowest energy level together. Fermions hate sharing space.
You're rugged individualists.
Precisely. Bosons, on the other hand, have integer spin. Photons are bosons, and crucially, axions are bosons. Bosons do not obey the exclusion principle.
So they are perfectly fine occupying the exact same space at the exact same time.
Yes. Now, under normal hot conditions, this doesn't change much. A warm gas of bosons bounces around like a normal gas, but a dark matter halo is incredibly cold.
Because as the universe expanded after the Big Bang, everything cooled down. The temperature plummeted.
And when you cool a gas of bosons to near absolute zero, their quantum behavior shifts dramatically. It comes down to their thermal de Broglie wavelength.
Okay, let's unpack that. In quantum mechanics, particles aren't just solid little dots, right? They act like waves.
Yes, and the wavelength of a particle is inversely proportional to its momentum. So as the axion gas cools down, the speed of the individual axions drops.
And as they slow down, their momentum drops.
Which means their de Broglie wavelength physically stretches out.
So the wave of each particle gets bigger and bigger as it gets colder.
Exactly. At room temperature, the wavelength of an atom is tiny. But in the freezing depths of a dark matter halo, these axion wavelengths stretch over macroscopic distances.
Until eventually, they stretch so much that they start touching.
They don't just touch, they overlap. The distance between the particles becomes smaller than the waves themselves. And when that threshold is crossed, the axions undergo a phase transition.
They become a Bose-Einstein condensate.
Yes. The billions of overlapping wave functions merge. The axions lose their individual identities completely. You no longer have a vast collection of distinct particles.
They have one single giant quantum entity.
Governed by a single wave function, the entire halo acts as one unified superfluid.
It's like imagine a crowded train station. Everyone is walking in different directions, bumping into each other. That's a normal gas.
Yeah.
But a Bose-Einstein condensate is like a flash mob. The temperature drops, the music hits, and suddenly billions of people are doing the exact same synchronized dance.
That is a brilliant analogy. They stop acting like individuals and become one giant entity. And we aren't talking about a microscopic drop in a lab. We are talking about a condensate spanning hundreds of thousands of light years.
It's just wild to think about. Quantum mechanics usually rules things small enough to fit on a pinhead.
Fair.
And here it is dictating the shape of an entire galaxy.
But this specific behavior is what provides the mechanism for the 9 rings. Because this galactic scale flash mob isn't standing still. It is rotating.
Right. The dark matter halo is spinning, and it has massive gravity.
So how does a smooth spinning sphere of axions develop distinct ridges? It comes down to orbital mechanics and the conservation of angular momentum.
Okay, break that down for us. How does the halo actually form?
It accretes mass from the surrounding space over billions of years. As axions fall inward toward the center of the galaxy, they bring angular momentum with them.
So as they fall deeper into the gravity well, they have to spin faster. Like an ice skater pulling their arms in.
Exactly. They fall in, spinning faster, but they don't just collapse into a black hole. They pass their closest approach to the center and get flung back outward on elliptical orbit.
Until they run out of energy and have to fall back in again.
Right. They travel outward until they reach their maximum distance, which we call the turnaround radius. At that exact moment, their radial velocity drops to 0 before they fall back.
So it's like throwing a baseball straight up. It slows down, hits the absolute peak of its arc where it hovers for a split second, and then drops. The turnaround radius is the apex of the orbit.
Yes. Now remember, the dark matter is a Bose-Einstein condensate. It is cold and 0 viscosity. The axions don't bump into each other and scatter.
They stay perfectly synchronized.
They remain on highly specific, coherent orbital paths dictated by their initial spin, which means you have massive, massive streams of axions all reaching their turnaround radii at the exact same geometric locations.
They all pile up at the apex at the exact same time.
And this is where the caustic forms. A caustic, in physics, is an envelope of focused particle trajectories. Think of the bright, curved lines of light you see at the bottom of a swimming pool.
The water bends the light and focuses it into intense, bright lines.
Right. In the halo, the axion orbits are focused. Because they all slow down and pile up at the turnaround points, you get a massive spike in physical density at those specific spherical boundaries.
But the halo is rotating, so they don't just pile up in a simple sphere.
Correct. The conservation of angular momentum deflects them laterally. The combination of falling inward and spinning sideways forces these density spikes to form into distinct concentric tubular rings around the galactic center.
So the dark matter actually stratifies into these nested layers.
It does. The continuous infall of dark matter creates multiple layers of these high-density turnarounds, and the geometry of these invisible rings is dictated by a very specific mathematical ratio.
And this is where the 2026 paper just blows my mind, because Sikivi and Zhao took this pure theoretical math for axion caustic rings.
And they overlaid it onto the observational data from the Yale team.
They put the theory over the reality.
Yeah.
And what happened?
The correlation was staggering. The radii of the 9 visible rings in LIDA 1313424 matched the predicted radii of the invisible dark matter rings with incredible precision.
The glowing galaxy we see is an exact map of the quantum dark matter halo we can't see.
Exactly. The geometry maps perfectly.
I want to make sure the mechanics of this are super clear. The caustic rings themselves are dark matter. They emit no light.
Right, they are completely invisible. But because they are zones of extreme particle density, they represent massive, concentrated trenches of gravitational pull.
They are deep gravity wells. And as the normal gas and dust of the galaxy orbits around,
The gas encounters these trenches, and it falls in,
it just gets trapped in the grooves.
gravitationally drawn right into the caustic rings. And once the gas is packed inside that high-density trench, it collides, compresses, and cools, which triggers intense star formation.
So the 9 glowing rings we see aren't the dark matter itself. They are just the visible matter lighting up the dark matter's invisible scaffolding.
It is exactly like scattering iron filings over a piece of paper with a magnet underneath.
You can't see the magnet, but you see exactly where the field lines are because the filings trace them.
The gas and stars in the Bullseye galaxy are the iron filings. The axion caustics are the magnet. And this elegantly solves the speed limit problem that ruined the collision theory.
Because the rings aren't rippling outward from a crash.
No, they are basically stationary architectural features of the dark matter halo. They evolve very slowly over billions of years, but they aren't fast-moving waves.
The visible gas just settled into the pre-existing gravity grooves.
Yes, there is no requirement for supersonic wave propagation, no catastrophic thermal unbinding. The physics works perfectly.
It totally reframes the history of the whole galaxy. It wasn't the victim of this violent, random, cosmic car crash. It's this highly ordered, quantum-sculpted record player.
A macroscopic quantum system.
But this raises an important question. If this axion model fits the data so perfectly, why are we only seeing 9 rings here? Why doesn't every galaxy look like a giant target?
That is the crucial caveat. The manifestation of these rings in the visible matter requires an exceptionally pristine environment.
Like it needs to be left alone.
Right. The dark matter caustics are probably present in most galactic halos. But the normal matter in the disk is subject to so many disruptive forces. Supernovas blowing up, internal turbulence, galactic bars, close encounters with other galaxies.
So if things get too chaotic, the gas just gets sloshed around and blown out of the neat little gravity trenches.
Exactly. The delicate imprint of the dark matter architecture gets completely washed out by chaotic, everyday physics.
So Leda 1313424 must have had an incredibly boring, isolated history.
It managed to avoid any major mergers or disruptions for billions of years. It allowed the gas to quietly pool into the axion trenches. It's a perfectly preserved fossil of the underlying dark matter geometry.
Which is why it's such a huge paradigm shift. It is a visible, large-scale proof of quantum mechanics. Because, for decades, scientists have been trying to find the axion in these deep underground labs.
Yes, experiments like ADMX, the Axion dark matter experiment at the University of Washington.
They use these massive, super-cooled magnetic cavities, right? Just hoping to catch a single axion flying through the Earth.
It is an incredibly difficult search because axions interact so weakly with normal matter. You were looking for a tiny signal barely above the quantum noise limit.
But Siki and Zhao's paper is basically saying, hey, we don't necessarily need to catch one in a jar to prove they exist. The actual structure of the universe is broadcasting it to us.
It flips the scientific approach entirely. Instead of looking for a microscopic particle to explain the universe, we are using the massive architecture of a whole galaxy to prove the particle. The macro observation validates the micro theory.
And if this holds up, it means dark matter is definitely a boson. It operates as a Bose-Einstein condensate, and it solves the strong nuclear force problem all at once.
It is a profound realization. One astronomical observation could resolve two of the biggest mysteries in modern physics.
So how does astronomy proceed from here? Because you can't just rewrite the textbooks based on one weird galaxy, right? Even if the math is perfect.
No, you absolutely have to verify. The immediate next step is a rigorous reevaluation of archival data.
Going back to the old photos.
Yes. Now that we have the mathematical blueprint for these caustic rings, astronomers will systematically look at the kinematic data of other known ringed galaxies, like the Cartwheel Galaxy or Hoag's object.
So the collision model might still apply to some of them, especially if they look messy.
Right. If there's an obvious nearby intruder galaxy, collisions are still a valid mechanism. But if we find that the radial spacing of the rings in those older examples also conforms exactly to the geometric ratios predicted by the axion model,
then it provides compounding evidence. We could start mapping dark matter halos just by reading the barcode of the rings.
We will also use new technology. With instruments like the James Webb Space Telescope and the upcoming Roman Space Telescope, our ability to see faint structures is exponentially greater than it was even 10 years ago.
So it's highly likely the Bullseye galaxy isn't alone. It's just the first one we had the tools to actually see properly.
As we look deeper, we are likely to find a whole population of these quiet, multi-ringed systems. And each new one will serve as a test for the condensate model.
And it helps the lab guys too, right?
Yes. The precise geometry of the galactic rings provides constraints on the exact mass of the axion particle, which tells the Earth-based haloscope experiments exactly what frequency to tune their machines to.
That is just a beautiful feedback loop. The galaxy tells the lab what to look for, and the lab eventually confirms the particle that shaped the galaxy.
It is a true synthesis of disciplines. We are moving away from this fragmented idea where cosmology is big and quantum mechanics is small. We are moving toward a unified framework where the subatomic laws actively build the cosmic architecture.
The narrative of space being this messy, chaotic demolition derby driven by brute force gravity, it's giving way to something so much more intricate.
The 12,220 kilometer per second problem forced us to look past the visible chaos. It forced us to recognize the invisible, freezing cold quantum fluid that actually holds it all together.
The baryonic matter, the stars, the gas, everything we can see and touch. It's just the indicator die revealing the hidden currents of the dark matter sea.
The Bullseye galaxy proves that order emerges from the quantum nature of the dark.
It just completely reorients how you have to look at the night sky. For centuries, humanity has mapped the stars, assuming those glowing dots of light were the main characters. We thought the visible matter was the substance of reality. But this whole discussion reveals that the visible universe is really just the decorative icing. The true physics, the massive structural scaffolding that dictates the shape and the movement of the cosmos. It exists entirely in the dark. So I want you to think about that. The next time you look up at a swirling galaxy or a starry sky, ask yourself, what else is out there? Silently choreographing the dance of billions of stars, completely invisible to your eyes.